Okay, let's unpack this. We've all heard that saying, right? We are drowning in information but starving for knowledge.
Hmm.
That tension, just the sheer amount of data versus, really struggling to get anything meaningful out of it, that feels like the core problem today.
It really is a structural issue.
So today we're going to dive into a methodology that's designed specifically to cut through that noise.
Right.
And it's not just about handling huge amounts of data, the petabytes. It's about making sense of maybe the most frustrating kind, small data, in what our sources call an ill-structured domain. We're looking at KDSM.
Yeah, and to really get why KDSM is needed, we first have to pin down the exact data problem it tackles.
Okay.
We're talking about repeated, very short serial measures with a blocking factor. Quite a mouthful.
Definitely sounds technical. Break that down for us.
Okay, so imagine you've got a data set. Let's call it matrix Y. These are measurements over time. Could be anything patient reaction time,
Yeah.
maybe a financial index.
Mm-hmm.
But here's the catch. You only measured it a few times, maybe 5, 6 times in a row.
Yeah.
That series, it's just way too short for, classic time series analysis.
Okay, too short for the standard tools and the blocking factor part.
Right. So all those little short series, they're grouped by an individual. We call that matrix X.
The individual, like a specific patient or maybe a town.
Exactly. A patient, a municipality, one factory. That's your blocking factor. And it means those 5 or 6 measurements from, say, patient A, they aren't independent.
Because they all come from patient A. They share patient A's characteristics.
Precisely. And if you just ignore that individuality, that blocking factor, well, your results are going to be flawed. Guaranteed.
So that sets up our mission then. We need to figure out how this KDSM methodology, knowledge discovery in serial measures and its software, Columbus, handle this tricky, non-independent data.
And how it actually delivered real insights, yeah, in some pretty critical fields.
So why do these traditional methods fail? Why can't we just throw standard statistics or, AI at this?
Well, they generally stumble in these ill-structured domains, these ISDs, because they just weren't designed for this specific combination of problems.
Okay.
Take classical time series analysis on the statistics side. It needs a decent number of observations, a reasonably long R, to estimate models properly.
Right.
With our tiny R, like 5 or 6 points, it's just not mathematically sound.
It makes sense.
And then there's this common workaround, Matthew's approach, where you try to simplify things. You take that whole series of measurements, matrix Y, and boil it down to one number per person.
Like an average curve, or maybe just the total change.
Exactly. But our sources call this a risk practice. Why? Because you lose a massive amount of information doing that. Really vital information.
The timing, the sequence of changes.
Yeah, all the dynamics get lost. And you often end up with conclusions that are, and I quote, very far from reality.
So simplifying it actually destroys the very thing you want to study, the change over time.
That's it. And, even if you did summarize it perfectly, you still haven't fixed that non-independence issue, the blocking factor.
Ah, right.
If you treat patient A's summary score and patient B's summary score as independent samples, you run straight into what the paper calls effect confusion.
Effect confusion, meaning you can't tell what caused the change.
Exactly. Was it the treatment you applied? Or was it just something inherent about patient A versus patient B? You can't separate them.
So KDSM has to somehow respect that individual structure, but still transform the data so we can analyze it.
That's the core challenge, and KDSM approaches it as a hybrid.
Okay, so KDSM is this hybrid solution, mixes AI and statistics. How does it actually work? How is it structured to get around that blocking factor problem?
Well, the overall goal of KDSM is pretty ambitious. It aims to produce an actual, explicit model of new knowledge.
Like a formal description of how things work in that domain.
Precisely. And it does this by integrating information from 3 different places. Matrix X, the individual characteristics.
The patient or municipality details.
Right. Matrix Z, which describes the event or treatment characteristics.
Like details about the therapy session or the training course.
And of course, Matrix Y in the actual measurements over time.
Okay, X, Y, and Z. How does it combine them?
Uses a 3-phase process. Phase 1 is BLA, baselines individuals analysis.
Baseline analysis, so looking at the start.
Exactly. It uses clustering techniques, AI stuff, to look at matrix X versus the initial state in matrix Y before any treatment or event happens.
Why do that first?
To identify different profiles of individuals right at the beginning, like are there distinct types of patients before therapy starts? This builds your initial knowledge base, KB0.
Okay, so BLA tells us who we're dealing with initially. But the real magic, you said, is getting around the blocking factor. That must be phase 2.
That's EEA, event effects analysis. And yes, this is really the heart of the methodology, designed specifically to neutralize that blocking factor. Instead of looking at the raw measurements in Y, KDSM calculates the differences between consecutive measurements for each individual. This creates a new matrix, matrix D.
Hold on, so if patient A had measurements M1, M2, M3, you don't analyze M1, M2, M3.
No.
You look at M2 minus M1 and M3 minus M2, the change between steps.
Exactly. You analyze matrix D, the matrix of differences.
Why is looking at the change, the difference, so powerful here?
Because the individual's inherent characteristics, that blocking factor, it's mostly constant over those very short time intervals between measurements.
Ah, okay.
By taking the difference, you effectively cancel out a lot of that constant individual-specific noise.
You strip away the static part.
Right. And what's left is primarily the effect of the event that happened between measurement 1 and measurement 2. You isolate the event's impact.
That is clever. Okay, so you've transformed the data with EEA. How do you get to the final knowledge, the actionable insights?
That's the third phase, KP, knowledge production.
Hmm.
Here, the goal is to interpret the results, particularly the patterns found in matrix D.
So interpreting the patterns of change.
Yes. They often use clustering again, but this time on matrix D. And crucially, they use illustrative variables from matrix X and matrix Z to understand what those patterns mean.
Connecting the change back to the type of individual and the type of event.
Exactly. And they often use a specific AI technique called clustering based on rules, or CLBR.
Clustering based on rules. What's special about that?
It lets experts inject some initial knowledge, that KB0 from the BLA phase, into the clustering process. It sort of guides the AI.
So the AI doesn't just find statistically valid clusters, but ones that actually make sense in the real world, like clinically or economically?
Precisely. It prevents discovering profiles that are just mathematical artifacts but don't mean anything practically. You end up with partitions, let's call them PE, that are both robust and relevant.
And all this is managed by the software, Columbus.
Yes, Columbus implements the whole KDSM process, and importantly, it includes specialized visualization tools, things like VAC and VI.
VAC and VIC.
Variability among classes, VAC, and variability inside a class, VIC. They're graphical techniques essential for interpretation.
Why essential?
Because they help you visually confirm if the clusters, the partitions you found, are actually meaningful and distinct. Are the groups really different from each other? High VAC. Are the members within a group reasonably similar? Low VIC. These graphs can be complex to make with standard tools like SPSS, but Columbus generates them.
Okay, let's make this concrete. Let's look at the first case study. Electroconvulsive therapy, ECT in psychiatry. Data from Barcelona.
Right, so the measurements here were psychophysiological specifically, reaction time, or RT.
Okay.
And the serial measures were extremely short. RT was only measured 5 times after each electroshock session.
5 times, like at specific intervals.
Yeah, 2, 4, 6, 12, and 24 hours post-shock. The individual patient was a blocking factor, matrix X. The shock itself was the event, linked to matrix C characteristics, perhaps, and RT was matrix Y.
What did that first step, the BLA phase, show about the patients before considering the shocks?
So clustering patients just on their baseline RTs, before the shock effects, it basically confirmed some clinical intuition, but put numbers on it.
Like what?
It clearly identified 2 main groups based mostly on age. You had young patients under 40 who generally had faster and more consistent reaction times.
Okay.
And then mature patients over 50 who had significantly slower RTs, especially on more complex cognitive tests. This split by age became part of the initial knowledge base KB0 used later.
All right, so that sets the stage. Now, if someone used traditional methods, they'd probably average the RT changes over all sessions for patient A and say, okay, ECT improved patient A's RT by this much overall.
Right. They'd create a summary curve per patient.
What did KDSM's EEA phase, analyzing the differences in RT between consecutive measurements, matrix D, reveal that the summary curve hides?
It revealed something pretty revolutionary, actually. It showed that the summary curve is fundamentally misleading. The analysis of the differences, session by session, showed that the very same patient often reacts quite differently to each individual electroshock session.
Wait, you mean their RT might get worse after one shock, but then much better after the next one? Within the same person?
Exactly. The change isn't necessarily steady or cumulative in a simple way. It depends not just on the patient, but seemingly on the specific shock event itself.
So the effect isn't monotonic, it doesn't just go steadily up or down, and it varies from session to session for the same person.
Correct. which implies that just averaging the effect across all sessions for a patient or looking at one overall curve misses the crucial dynamics.
Wow, that seems huge. If the effect varies like that session by session, the whole idea of analyzing one average patient curve is, well, flawed.
Absolutely. The source material states this non-monotonous behavior was basically undocumented before this analysis.
So what's the implication?
It really suggests a need to change how ECT effects are studied and maybe even managed. If the impact can vary so much session to session, you might need to monitor and potentially adjust things much more dynamically.
That's a powerful insight directly from handling the data structure correctly, isolating the event effect. Okay, that's psychiatry. Can KDSM deliver similar kinds of structural insights in a completely different field? Like, say, labor economics. Let's look at that second case, evaluating unemployment training programs in Chihuahua, Mexico.
Yeah, a totally different domain. Here, the aim was to gauge the effectiveness of a program called the Training Scholarship for Unemployed Workers, TSUW.
And the measurement.
It was the Contracting Index, CI, basically a measure reflecting job placements linked to the program.
And again, short serial measures.
Very short. CI was measured only 6 times over a 3-month period following the training courses.
Okay. And the complexity here.
The big challenge was integration. You had 3 sort of incompatible sets of information. Matrix X described the individual municipalities, the blocking factor here, reflecting local economic conditions.
Right.
Matrix Z described the training courses themselves, things like the subject taught, or whether it was classroom only or involved companies.
And Matrix Y was the CI scores over those 6 time points.
Correct. KDSM had to integrate X, Y, and Z. It used that CLBR method, the clustering based on rules, and the experts provided initial rules, KB0, based on known factors like territorial stretching and the local economically active unemployed population, EAUP.
So biasing the clustering towards economically meaningful factors.
Okay.
They calculate the differences in CI, matrix D, to neutralize the general economic vibe of the municipality. What actionable results came out of the final step, the knowledge production?
So the analysis clustered the courses into different groups based on how the CI changed over time, based on matrix D. 2 classes really stood out and told very different stories. First, there was Class D. This was like the immediate success story. Courses in this group showed consistently strong, positive differences in the contracting index, and quickly.
Things got better fast. And did KDSM figure out why? What kinds of courses were these?
Yes, using the matrix Z variables, it identified these Class D courses as predominantly being the mixed modality type,
Mixed modality, meaning?
meaning they involved collaboration with local private companies, maybe internships or direct placements.
Sure.
These courses were incredibly effective. Nearly 90% of participants found jobs.
Wow, that's a crystal clear signal for the Secretary of Labor there. Get private companies involved for fast results. What about the other main group? You said there were 2.
The other major group was Class U. Now, these courses also showed success, but in a very different pattern.
How so?
They showed a belated recovery in the CI. The positive differences, the job gains, didn't really show up significantly until around the 60-day mark. It took longer.
Interesting. Delayed effect. Did KDSM identify what type of courses these were?
Overwhelmingly, yes. Class U courses were predominantly focused on self-employment training.
Ah, that makes perfect sense.
Exactly. The insight is crucial. People trained for self-employment naturally need more time to actually set up their business, get clients, and then show up as employed in the contracting index.
So it's not that the self-employment courses failed. They just had a different, slower success trajectory.
Precisely. And this is super relevant for you, the listener, especially if you're involved in policy or program evaluation. KDSM didn't just give a thumbs up or thumbs down.
Great, it nuanced it.
It said, look, the mixed courses give you quick ROI. The self-employment courses work too, but you need patience. That allows administrators to make much smarter decisions about budgets, program mix, and managing expectations.
So let's bring this all together. We started with this really frustrating data problem. Short, non-independent measurements, complicated by individual factors.
Yeah, the kind of data that often gets simplified incorrectly or just ignored.
And we found KDSM offers this general framework. It's not just one technique.
Right, it's a methodology. It cleverly combines specific AI tools like that rule-based clustering, CLBR, uses solid statistical tests for validation, and relies on those visualizations, VAC and VIC, to make sense of it all.
And the key transformation seems to be that difference calculation, creating matrix D.
Absolutely. That's what isolates the event effect from the individual effect. That seems to be the core trick. And the source emphasizes it's a framework applicable in any field where you have data structured like this XYZ with those very short serial measures.
Now, the examples we used, ECT and job training, the serial measure was time. Hours after a shock, days after a course.
Temporal sequences.
But the source material hints KDSM might be even more general than just time-based sequences.
That's right. And that leads to a really interesting question for you to explore further. KDSM isn't necessarily limited to time.
How so?
Well, imagine an image processing problem. Instead of time, your serial measure could be something like the pixel count at each of 16 different gray levels.
Okay, so measurement 1 is count for gray level 1, measurement 2 is count for gray level 2, up to 16, a sequence but not time.
Exactly. It's an indexed attribute. Now, if KDSM could analyze the differences or patterns across that sequence of 16 gray levels, comparing different images, X, perhaps taken with different camera settings, Z.
It could potentially find patterns in image textures or compositions that aren't obvious otherwise.
Precisely. So the final thought for you is, if KDSM can work with non-time-based sequences like gray levels, what other kinds of sequential or indexed data we don't normally think of as a series could this methodology unlock?
Interesting. What other hidden structures are waiting in seemingly non-sequential data? Something to definitely mull over until our next deep dive.